Hello and welcome. This is going to be our lecture video for this worksheet, Coulombic attraction. Let's go ahead and get started with number 1 here. What subatomic particles do these symbols represent? So the positive charge, that is a little bit larger, is definitely a proton. The negative charge, that's a little bit smaller, is an electron. They have the same amount of charge. The proton is about 1,000 times bigger than the electron, though. Interesting fact. All right. Would you expect to observe attraction or repulsion? We're going to go with attraction. Opposite charges attract. What are the independent and dependent variables? What's actually changing is the distance. The distance between our positive and our negative particles. And then write a sentence that describes the observed relationship between the independent and dependent variables. All I'm going to say is shorter distance leads to greater attraction. And you can see that because as the distance gets smaller and smaller, the force of attraction, that number is going up. All right, if the distance between a proton and electrons is 0.5 nanometers, what would you expect the force of attraction? Would you expect it to be greater than or less than 0.26 times 10 to the negative 8th newtons? Let's look back at this last example. So when the distance is 0.3 nanometers, the force is exactly 0.26 times 10 to the negative 8th newtons. So if we have a greater distance, then we are going to get less force. So definitely less. All right, if two protons, and this is easy to miss, it says two protons are 0.1 nanometers away from one electron, would you expect the force of attraction to be greater than or less than 2.3? So that's the same distance as that top example, but we've now added an extra proton. From what I know about magnets, it makes sense that this would be greater, that including an additional magnet is going to increase the force of attraction. All right, on to Model 2, the alkali metals. So consider the diagram in Model 2. What do the arrows represent? So the arrows, how thick they are represents the force of attraction. All right, how does the thickness of the arrow relate to the property given in part A? So a thicker equals stronger. All right, use the periodic table, locate the elements whose atoms are diagrammed in Model 2. Are the elements in the same column or the same row? They're the same column, which we also call a group. We've actually rarely called them columns, we almost always call them groups. All right, circle the outermost electron in each of the diagrams in Model 2. So it wants us to come back up here and circle the outermost electron. Another word for this is it's the valence electron. And you can have up to 8 valence electrons on an atom because these are all in group 1. They all have 1 valence electron. As you move from the smallest atom to the largest atom in Model 2, how does the distance between the outermost electrons of the nucleus change? It increases. All right, as those inner shells get full, the valence electrons have to be further and further away from the nucleus. All right, as you move from the smallest atom to the largest atom, how does the attraction force? It decreases, which makes sense with what we know about the impact of distance. That greater distance is going to lead to less attraction force. Are your answers consistent? I'm just going to say yes. All right, now Model 3 is going to help us investigate the number of protons and the attractive force. So we've got that Model 3 to look at. What are the independent and dependent variables? So the independent is number of protons, and then the dependent is the strength of the force. Write a complete sentence that describes a relationship. So as number of protons increase, the force of attraction does too. So they increase together. What would be the attractive force on a single electron of 5 protons or in the nucleus of an atom? So let's take a look at the pattern here. We have all the way up till 4. So with 1, it's 2.3. Ignore the scientific notation because it's all the same here. For 2, it's 4.6. For 3, it's 6.9. For 4, it's 9.2. Every single time it's counting up by 2.3. So if we count up by 2.3 again, 9.2 plus 2.3, we'll get 11.5. And then we'll add in that times 10 to the negative 8th newtons. All right. Imagine that a second electron was placed to the left of the nucleus containing 2 protons. Model 3, set D. Predict the force of attraction on both the original electrons and the second electron. So here we got to kind of make a prediction. But what I know about magnets is that they don't have to share their charge, meaning that all of the charge, the power to attract negative charges, doesn't just get directed to one electron, and then when another electron comes in, it has to be split up. It's going to be the same amount of charge, the same amount of pull in all directions, regardless if there's any electrons out there. So if this force of attraction is 4.6, then if another one comes in, it would be another 4.6 times 10 to the negative 8th newtons. All right, and so to read this here kind of confirms what we thought for that last one. Just notice here that the force is not divided up amongst the electrons in the atom. So here with problem number 12, we see that the distance matches model 3. There's 3 protons in the middle. So the approximate attractive force on all of these is going to match what it was in model 3, which was 6.9 times 10 to the negative 8th newtons. So 6.9 times 10 to the negative 8th newtons. And that's for this one, and this one. Doesn't matter where they are. They're all experiencing the same force of 6.9 times 10 to the negative 8th newtons. Now that 6.9 would be diminished very slightly by the repulsive forces of the electrons on one another, but not very much at all. All right, on to model 3, where we have 3 different elements, all from the same period. So using the periodic table, look at the elements whose atoms are diagrammed here. Are the elements in the same column or same row? It is the same row, which we call a period. Circle the outermost electrons. So sodium has just the 1. Aluminum has 1, 2, 3 valence electrons. And chlorine has 1, 2, 3, 4, 5, 6, 7. All right, so all of these are in the same energy level and are going to experience the same attractive force from the nucleus. Which of the 3 atoms diagrammed in model 4 has the strongest attraction for its outermost electrons? This one is going to be the chlorine. The reason for that is chlorine, being atomic number 17, has 17 protons in its nucleus. Sodium is atomic number 11, so it only has 11 positive charges. And these energy levels are still at the same distance. This is just energy level 3. So it's probably approximately 0.3 nanometers away from the nucleus. So if these are all the same distance, but the charge is increasing, then it's going to have a much stronger force of attraction. All right. As you move from the smallest atom to the largest atom, does the distance between the outermost electrons in the nucleus change significantly? No. They're all part of the same shell, is how we can think about that. Can the differences in the attractive forces shown by the arrows be explained by a change in the distance between the electrons and the nucleus? No, because they're all the same. I actually didn't even notice that the arrows were different widths. Yep, and that confirms what I said up here. It's definitely chlorine. It's got the widest arrow there. On the diagram, write in the number of protons located in the nucleus of each atom. We already did that for these two. Let's add that in for aluminum. Aluminum is going to have, let's see, atomic number 13, 13 protons there. Can the differences in the attractive forces be explained by the change in the number of protons? Yes. More protons equals greater force. All right, so for each of the elements below, circle the element whose atom will have the strongest attractive force between their outermost electrons and the nucleus. So barium and calcium. They are both group 2, but barium is much further out, so its valence electrons will be further away. Calcium wins that battle. Chromium and copper, let's see, they're part of the same period, but copper has many more protons, so copper's going to win that battle. Argon and xenon, they're part of the same group, but xenon is further down, so argon will have the shorter distance and therefore the greater attractive force. All right. Extension question 18 asks you to flip back to model 2. I can't do that super easily here, so I'll just write it here. Write the number of protons in the nucleus of each atom. We have lithium, which has 3 protons, atomic number 3. We have sodium, which has 11 protons, atomic number 11. And we have potassium. Potassium will have 19 protons, atomic number 19. When comparing elements in the same column of the periodic table, which factor, distance of the nucleus or number of protons in the nucleus, seems to be the dominant factor for determining the attractive force? It is the distance. And one way we can tell that is from part A here. We have more protons in potassium than lithium, but the diagram shows us that potassium has a weaker force. So clearly the greater number of protons isn't overcoming that greater distance. So distance is the dominant force. All right. Consider the data presented in models 1 and 3. Describe the mathematical relationship between distance and attractive force. We're going to say that this is an inverse relationship. It's a good math word to describe how as the distance goes down, attractive force goes up. And then number of protons and the attractive force, we're going to call that a direct relationship, which is a good math word to describe how as one goes up, the other goes up. And more protons leads to greater attractive force. We'll call that good for this lecture video. I'll embed a few more questions for you here. Have a good rest of your day.